Welcome back. It's time for video 3 from Unit 2. We're going to swing our focus into Section 2.2, start working on sets and set operations. So with no further ado, let's head out to the old PowerPoint opportunity here. All right, let's go from the current slide. Okay, so you can see we're moving into Section 2.2 where we will spend some time describing sets. So for right now, sets are collections of items. Some books call them elements. All right, so some info about sets. There are things called infinite sets and finite sets. So we'll look at the difference between the two. We'll look at what it means to have for two sets to have a one-to-one correspondence. Okay, a set's just basically any collection of objects. They don't have to be mathematical. They don't have to be numbers. You could have a set that consists of your favorite baseball teams. You have a set that consists of your favorite people in the world. So in that sense, sets aren't uniquely defined mathematically. The elements or the members or the things that make up the set, the order in which they're listed doesn't matter at all. Generally, sets are named by a capital letter, and you separate the members of the set by commas, and you use those braces that it seems like only math teachers can make. Okay, so here we go. Some examples. So we're going to have a set that consists of Dr. Firster's favorite sports teams. I cleverly called this S for sports, but again, there's nothing unique about that naming. This set contains three elements: the Packers, the Celtics, and the Phillies. They do happen to be three of my favorite teams. So again, the order in which they're listed doesn't matter. If someone had listed Phillies first and then Packers and then Celtics, it still names the same set, right? So when you list elements of sets, order isn't significant. A second example, the days of the week. If you really want to bother somebody, list these things any way other than the way they're currently on the screen. They just get upset. So I cleverly called this W for week, I guess. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Both of these set examples are finite. There's a fixed number of elements inside the set. Last but not least, the set of prime numbers. You knew it was math class. I had to throw something in that was mathy. So prime numbers, for those of you who know, are numbers that have only two divisors, the number itself and one. 2 is a prime. In fact, it's the only even prime. 3, 5, 7, 9 is not prime because 9 has a factor other than 9 and 1, specifically 3. So there you got the dots on the end that seems to indicate this is not a finite set. It does not end. Notations. This is actually, I believe, the Greek letter epsilon. So we use it to represent is a member of or belongs to a given set. So the example in front of you says, if set A contains the numbers 2, 4, 6, and 8, the statement that says 2 is an element of A would be correct. 5 is not an element of A, and that's also correct. And as in many math symbols, if we slash it, we just negate. You're familiar with not equal to, which is just a slashed equal sign. So in this case, we're slashing that is an element of, and that second component would say 5 is not an element of A. And that's also a true statement if set A is described as above. When we talk about sets, they must be well defined. There can't be any nebulous nature. Everyone would have to agree that this is in the set or not in the set. So in terms of well defined, the people who have Dr. Firster for Math 109 is a well defined set. There's no ambiguity. You either do or you don't. We can look it up on the computer system and we can find that your name is included, but probably Brett Favre's name is not because he's not listed as a student in Math 109. Something not well defined, the short people at Immaculata. And you already knew that. I mean, who's to determine what short is? Is it less than 6 feet? Is it less than 5 feet? It's too vague. So it's not a well-defined parameter set for that set. More some notations. We've met the ellipsis before. Generally continues and says in this trend, you've got continuing onward. Ways that we can represent sets. We can list them. All right, we can provide the roster. That's kind of what we've seen in that last couple of examples. And we can also look at set builder notation. If any of you ever looked in the back of your algebra book back in the day, you may have seen set builder notation writing sets for some of your algebra exercises. We'll visit that coming up as we look. It's probably a little harder. All right, here's a set builder notation example. All right, and I'm going to go ahead and tell you how we read it. So that defines the set. In this case, it's set C is equal to, obviously, no fake, the set of, with the braces, all elements X. Now, X isn't special here. It's a placeholder. So you could have called any letter here, but what follows that big vertical, which is read such that, is a condition that identifies who is or isn't a viable player for X. In this case, X has to be an integer. So things like fractions and decimals like 0.2 are no good. They're not integers. And there's an additional condition out there in that X, whatever it is, has to be less than or equal to 4. So if we were to try to list the elements of this set, in other words, provide the roster, we could if we've correctly identified all of those components for that notational building example set. We'd now start listing integers and make certain that the integers that we listed are in fact all 4 or less. All right, so here is a roster for set C. Again, some of you are not as familiar with the dots on the front end of that set. So you might have been happier had I started 4, 3, 2, 1, 0, and then ran the dots on the right side showing a decrease one by one. I tended to show it the other way. Either way is acceptable mathematically. So that's set builder notation translating out to roster notation. All right, we're going to try it again. You ready? There's our set builder. Okay, so C names the set. K is a placeholder. All right, so we're going to do whatever 2K plus 1 does. But please notice there are only specific values for K that are legal, specifically 4, 5, 6, and 7. So if we put 4 in for K and multiply it by 2 and then add 1, we'll get 9. We put 5 in for K and multiply it by 2 and add 1, we'll get 11. And I'll let you do your own mathematics. So the only possible values at K were 4, 5, 6, or 7. So we have a very concise set C, containing a 9, an 11, and a 13, and a 15. This is a finite set. It has only 4 elements. All right, what do you got for me, Dale? Well, I'm looking for a set J such that J is an even prime number. Well, if you were paying attention a moment ago, you know this is not a very extensive set. It's got 1 element. 2. There are lots of prime numbers. In fact, the set of primes is infinite, but it doesn't have very many elements who are even. Only 2. Okay, we're going to go the other way. We're going to give you the roster and try to write the set builder. So get a good look at it, draw some conclusions. Looks like they're all evens. Looks like it goes on and on and on. Be careful about 0, all right? So if you're going to say these are positive, well, what about 0? Is 0 positive? By definition, most books say 0 isn't positive. So I went ahead and said this is the set X such that X is an element of the positive even integers. That's not all you could have written. Had you written something different, as long as it accurately described that set and nothing else, I would have given you credit for it. A little different here. Well, what do you got? Well, it looks like they're all odds. So maybe we'll have something that mentions odd integers, but it's not all of the odd integers. It's only certain ones that are as small as 3 and no bigger than 17. So look at this. We're going to say set X such that X is odd. It's an odd integer. And then we're going to put that second condition on. X has to be trapped between. So it has to be greater than or equal to 3. Has to be less than or equal to 17. And that's good. Equal sets. 2 sets are considered to be equal if they contain the exact same elements. Now remember, the order in which these elements are listed doesn't matter a hill of beans. All right, so if you say, well, my set has a 2 and a 5 and a 7, and Susie says, well, mine has a 7 and a 5 and a 2, your set and Susie's sets are equal. They contain the exact same elements with no preference to order. All right, equals different than one-to-one correspondence. If sets are in a one-to-one correspondence, they can be paired up so that for each element of A, you can find an element of B. Exactly one pairing, one-to-one. Okay? So first of all, if 2 sets are in a one-to-one correspondence, they don't have to be equal. but they have to have the same amount of terms. They have to have, again, I'm going to cheat and throw you a word here that we'll catch later. They have to have the same cardinality. They have the same number of terms in the sets. An example for you. First set consists of 4 people: Bailey, Izzy, Maeve, and Tiara. They're going to match up with famous or favorite actors. You got Tom Cruise, Denzel, Harrison Ford, and Tom Hanks. And you're supposed to list one possible one-to-one correspondence. Well, you just got to pair them up. So Bailey, God bless her, she could pick any of those 4 actors and said, I want to be paired with Denzel. Cool. As soon as Bailey picks Denzel, none of the other 3 people in that first set can be paired with Denzel. Denzel's taken. So when Izzy picks, she could pair with Tom, or she could pair with Harrison, or she could pair with Tom Hanks, I should say, but she can't pair with Denzel. So as the pairings are started, the number of options diminishes by 1 each time. So again, we got Bailey with Denzel. Let's take Izzy and put her with Tom Cruise. Then when it's Maeve's turn to pick, she's down only 2 choices. She's got Harrison Ford or Tom Hanks. And whoever Maeve takes, the last one left is for Tiara. So the question is, how many such correspondences are there? Well, if you remember, Bailey had 4 to choose from, but Izzy only had 3, and Maeve only had 2, and Tiara only had 1. So we're going to see on the next slide that the way we decide how many correspondences that there are is by multiplying those options together. So it's going to be 4 times 3 times 2 times 1, and you guessed it, that's 24. I'll bet that's what it says. Oh my gosh. If there were 5 in each set, the first guy would have 5 choices. Next guy would have 4, and then 3, and then 2, and then 1. 5 times 4 times 3 times 2 times 1, you guessed it, it's 120. For those of you who met factorials back in your high school setting, that's exactly what you see here. 4 factorial is 24, 5 factorial is 120. All right, what did you just do? You just did the fundamental counting principle. Your author describes only 2 things, so he calls one event M and the other event N. This can be extended for any number of possible events, and you would simply continue multiplying. That's kind of what we saw in our last example. So if you do one of them M ways and another one N ways, the 2 together can be accomplished the product of M times N ways. Some of you remember tree diagrams from back in the day. Looks like the first event here seems to be tossing a coin, and you get a head or a tail, and then it looks like somebody threw a die, and you could get anything from a 1 to a 6. And this lists all of the possible outcomes. All right, so it's a really cool visual. It can be painful if the events have a lot of possible outcomes. Equivalent sets with the little squiggle. 2 sets are said to be equivalent if there is a 1-to-1 correspondence between the sets. I think an easier way to approach this is, do the 2 sets have the exact same amount of elements in them? Do they have the same cardinality? If they do, they're equivalent. All right, now catch these last 2 questions. If 2 sets are equivalent, must they be equal? No, they just have to have the same amount of elements. One set could list football players, and the other set could list numbers, right? They won't be equal, but they may contain the same amount of elements. If 2 sets are equal, must they be equivalent? Yes. If the 2 sets are equal, they contain the exact same elements, so they would have the same number of elements. So if they're equivalent, they do not have to be equal. But if they are equal, they do have to be equivalent. That, my friends, wraps video 3 from Unit 2. We'll be back shortly with video 4 from Unit 2. See you then.